A stroke is when blood flow to part of the brain stops. This simple interruption sets off a devastating chain of events. Without a constant supply of blood, brain cells are starved of the oxygen and nutrients they need to survive. They begin to struggle, and then they start to die. This cellular death results in a sudden loss of brain function. A person might abruptly find they cannot speak, or that one side of their body will not move. Their vision might blur, or their thoughts might become jumbled and confused. It is a sudden, silent internal emergency that unfolds within the delicate tissues of the brain. There are two main ways this crisis can happen. The first and most common path is an ischemic stroke. Think of this as a plumbing problem, a blockage in a critical pipeline. A blood vessel that feeds a part of the brain becomes clogged, and blood can no longer pass through. The second, less common path is a hemorrhagic stroke. This is not a blockage, but a rupture. A blood vessel inside the skull breaks open. Blood spills into the brain tissue, causing damage through pressure and toxicity. Both types are medical emergencies, but they begin from different failures in the brain's vascular system. Understanding these two types is crucial because they require different treatments. An ischemic stroke begins with a vascular blockage. This obstruction can form in several ways. Sometimes, a blood clot, known as a thrombus, develops directly within one of the brain's arteries, often in a vessel already narrowed by atherosclerosis. This process is called thrombosis. In other cases, the blockage travels from another part of the body. A piece of a clot from the heart, a fragment of plaque from a large artery breaks free and journeys through the bloodstream, becomes lodged in a smaller brain artery. This is an embolism. In rare instances, a severe drop in the body's overall blood pressure can starve the entire brain of adequate flow, a condition called systemic hypoperfusion. Once blood flow is cut off, a toxic sequence called the ischemic cascade begins. The first step is an immediate energy failure. Brain cells, or neurons, are incredibly active and demand a huge amount of energy in the form of a molecule called ATP. Without oxygen from the blood, they can no longer produce ATP. This energy crisis causes critical cellular machinery to fail. One of the first systems to break down is the sodium-potassium pump. This pump is responsible for maintaining the delicate electrical and chemical balance of the cell. When it stops working, sodium ions flood into the cell and water follows, causing the cell to swell dangerously. This cellular swelling and energy failure lead to the next destructive step. The cell membrane loses its normal electrical charge and depolarizes. This uncontrolled electrical firing causes the neuron to release massive amounts of a neurotransmitter called glutamate. In a healthy brain, glutamate helps cells communicate, but in these excessive amounts, it becomes a poison. It overexcites neighboring neurons by binding to their receptors. This overstimulation, known as excitotoxicity, is a key driver of cell death in a stroke. The brain's own communication system is turned against itself, spreading the wave of injury outward from the initial site of the blockage. The flood of glutamate triggers the final, fatal stages. It opens channels on the surface of other neurons, allowing a massive influx of calcium to pour into the cells. Healthy cells keep their internal calcium levels extremely low, but this sudden surge activates a host of destructive enzymes. These enzymes begin to systematically dismantle the cell from the inside out. They chew through the cell membrane, break down essential proteins, and damage the cell's DNA. This cascade of damage also produces highly reactive molecules called free radicals, which cause further injury through oxidative stress. Eventually, the cell succumbs to this onslaught and dies, a process that can also trigger inflammation, worsening the damage to surrounding tissue. In the center of the stroke, where blood flow is completely or almost completely gone, brain cells die within minutes. This area of irreversible damage is known as the ischemic core. Surrounding this core is a region of tissue called the penumbra. Cells in the penumbra are in trouble. They are not functioning, but they are still alive. They are stunned, existing in a state of low energy with just enough blood supply to survive for a short time. This penumbra is the primary target of emergency stroke treatment. The entire goal of rapid medical intervention is to restore blood flow to this area, to save these vulnerable but salvageable cells before they, too, become part of the dead core. The most effective way to save the penumbra is to restore blood flow, a process called reperfusion. This can be achieved with clot-busting medications procedures that physically remove the blockage from the artery. When successful, reperfusion allows oxygen nutrients to reach the starving brain cells, giving them a chance to recover and survive. This is why time is so critical. The longer the penumbra goes without blood, the more of it will be lost. The window of opportunity to save this tissue is precious and short. Swift action can make the difference between a minor deficit, a devastating permanent disability by rescuing this at-risk brain tissue. However, the return of blood flow carries its own risks. This phenomenon is known as reperfusion injury. While oxygen is essential for cell survival, its sudden reintroduction into the damaged, chemically unstable environment can be harmful. The returning oxygen can react with other molecules to create a massive burst of destructive free radicals, intensifying the oxidative stress on already weakened cells. Section 4. The bleed. The mechanics of hemorrhagic stroke. A hemorrhagic stroke occurs when a blood vessel within the skull weakens and bursts. Unlike an ischemic stroke caused by a blockage, this type is caused by a leak. Blood escapes the confines of the artery and spills directly into or around the brain tissue. The most common cause of this rupture is chronic high blood pressure or hypertension. Over many years, high pressure relentlessly batters the walls of small, delicate arteries. This causes them to become brittle and prone to breaking. Another major cause is a ruptured aneurysm, a weak balloon-like bulge in an artery wall that can suddenly give way. Other, less common causes can also lead to a bleed in the brain. Arteriovenous malformation, or AVM, a tangled, abnormal connection between arteries and veins that bypasses capillaries. These vessels are weak and can rupture. Severe head trauma can tear blood vessels, causing bleeding. Anticoagulant medications, or blood thinners, can increase the risk of hemorrhage. While these drugs are vital for preventing clots, they can turn a minor bleed into a life-threatening hemorrhage by stopping clotting. Once a vessel ruptures, the damage occurs through several mechanisms. First, mass effect. The accumulating pool of blood, called a hematoma, acts as a growing mass inside the rigid skull. It compresses and displaces the brain tissue around it. This pressure can injure neurons and disrupt their function. As the hematoma expands, it increases pressure inside the skull. Section 5. Conclusion. The race against time. Whether caused by a blockage or a bleed, a stroke is fundamentally an attack on the brain's oxygen supply. Neurons are exquisitely sensitive to this deprivation. Within minutes of losing their connection to the bloodstream, they begin a cascade of self-destruction. The ischemic core represents the territory that is lost almost immediately, a zone of irreversible death. But around it lies the penumbra, a battlefield where millions of brain cells are struggling to survive. This is the area where medical intervention can make a profound difference, where the outcome of a life can be rewritten. The core mission of emergency stroke care is to protect this vulnerable tissue. For an ischemic stroke, treatments are designed to dismantle the blockage and restore circulation to the penumbra before it perishes. This can involve powerful clot-dissolving drugs or intricate endovascular procedures to retrieve the clot. For a hemorrhagic stroke, the focus shifts to containing the damage. Doctors work urgently to control blood pressure, reduce the swelling inside the skull, and sometimes perform surgery to remove the hematoma and relieve deadly pressure. In both cases, the strategy is defensive, aimed at limiting the expansion of the injury. The process of brain injury during a stroke is swift and unforgiving. The damage spreads like a fire, consuming brain tissue with each passing minute.